let me introduce Anna Aguiar. So she's a professor at FEUP, and is going to give a talk on 5G new radio unlicensed with OAI. Anna has a lot of experience using OAI, and we have been in Always Smart working with your team on this use case. It is quite interesting because we also, as OAI box providers, face the challenge that many labs doesn't have a trial license on 3GPP. So having spectrum available in a license bands could be a way to facilitate experimentation using the existing Wi-Fi bands to test 5G end-to-end. So Anna will give you an examples and practical insights about unlicensed 5G.
Thank you very much for the introduction, and just heads up, thanks a lot to Philippe for the slides and for the demo yesterday, if you had the chance to look at it. So he has been developing this for a long time within 2 projects so far. And let's start with first, why 5G unlicensed? Our main motivation initially was that in Portugal, the regulator sold all the spectrum. So there were no licenses left over for non-public networks. So we looked at, so let's do this on the unlicensed spectrum. That was the initial project when we started, okay? The other idea is that you can actually have this in environments that are not very crowded. Okay, and it's less costly. You do not have to buy a license. You do not have to go through the procedure. And somebody was telling me yesterday that when they try to sell the industrial use cases to companies, the only thing they say is they want it cheaper, cheaper, cheaper. And so, look, well, if you can support the traffic and carry the traffic, this is going to be cheaper than a licensed spectrum. Okay, so that is the motivation behind it. The spectrum is there. You can use it under certain constraints. So we started looking at how we could use it. And it was critical to have OAI for this because we can touch the code base. Otherwise, there would be no way to go about it besides doing simulations, right? I'm not very fond of. So that was the first thing. I'm going to have a problem. I cannot even see my slides. I'm tired and I cannot see anything. Well, it's better like this. Okay. So these were the main motivations behind it. So we need to be aware that there are these limitations. Okay. The usage of the unlicensed spectrum is regulated also. So you have power limits. You have duty cycle limits. Sometimes you have power control limits. You'll have listen before talk. So it's not like you can go ahead and just do TDMA and use it all the time. So that's the trade-off. And this also limits where you could use it. So we need to have low contention environments. So the use cases we are thinking of are industrial IoT in the sense of using IoT scenarios. So short packets, nobody will occupy the channel for a very long time, so that you can meet these regulatory requirements for the unlicensed spectrum. Now, after you do have the channel acquisition, then you can have a lot of things that 5G provides, and that usually what is the competing technology is Wi-Fi does not provide by itself, right? So you can have end-to-end QoS. You can, well, at least some, not everything, but you can have some QoS. You can have network-controlled mobility, so much it's embedded in the cellular stack. You can have all this multi-connected, so bearer aggregation, all the different slicing, GSN, AAA, which is something that is not straightforward with Wi-Fi. And you can actually also use this unlicensed spectrum just as an additional spectrum in a regular operator that has actual spectrum. Because even inside operators, sometimes for specific projects, they would like to have spectrum and the other guys don't give them and they are fighting internally for spectrum. So I think there will be use cases from our experience. There will be use cases for this technology. So first thing, some background, so what spectrum we are talking about? We are talking about this uni band, so up from the 5 gigahertz band, and now going up to 7 gigahertz. Although one of the limitations you have in the unlicensed spectrum is that the regulation is not the same everywhere, right? This is not, you have, I'm just giving 2 examples here. You have something for Europe. Europe has not regulated above 6 gigahertz yet. The US has already produced something above 6 gigahertz, and these rules will likely not be the same everywhere. So it's a bit different. We'll have to deal with that. Now, just as a background, as I said, you can use the New Radio unlicensed. Everywhere I have NRU is New Radio unlicensed. You have the anchored versions. This means you are using the unlicensed spectrum only for the data plane. So you keep your control plane on the licensed spectrum attached to a regular operator, and you just use this as a complement. Or you can use it as a standalone. What we did was standalone. So we have both the control plane and the data plane on the, so it's a full non-public network on unlicensed spectrum. Again, where am I moving backwards? Okay. So then we have a look at the 3GPP. And the NRU was standardized in release 16, and it's been there since release 16. There have been no significant updates, because I don't think there are many people working on this. But it's so it standardizes mainly 3 things: the PHY processes, the MAC procedures, and then the radio resource control. And we're going to be briefly over what is there in each of them. So for the physical layer, it specifies sensing slots, so the size of the sensing slots. 2 types of access, one with random backoff and some kind of a short sensing, so once you have the channel so that you can keep the channel. Then maximum occupancy. So at some point, if you acquire the channel, at some point you do have to leave it. You cannot just, because you acquired, just keep going. There's a maximum amount of time you can use it, then you need to leave. Then energy threshold is not fixed. It should be adapted to your circumstances, and this is one of the tricky things of this. Another thing it's standardized is to increase the SSP candidate slots, and this is because sometimes you might not be able to transmit, so you might lose your sync between the UEs and the G node B. So it's standardized that you can have more options for sending the SSPs, synchronization signal. It also allows you, so we need to do channel sensing, and when we do channel sensing, we can measure only the energy of the resource. So this is in the standard. This is not, we didn't invent it. Initially, we were measuring everything, but you can actually, per standard, measure only the resource blocks that you are going to transmit on. And this is important for speeding up the channel, the clear channel assessment. So less samples, less computation. And this is, and by the way, there's something else that's not here. You can, once you sense it, the response can use the same resource blocks. So it's, you can, both ways. Then for the MAC, most important things, you need changes on the HIRQ, because if you cancel a transmission for some reason, your HIRQ is going to think there were block errors. So it's going to downgrade your MCS until you're really very, very slow, although it's not a problem of the channel, it's a problem of contention. So you need to change the MAC to adapt the HIRQ to that. Simon is doing that. Simon is over there. And then the RRC layer, it's actually only there for configuring all the parameters of the sensing, the frequency bands, and the bandwidth part to fall back to when you lose the channel for too long. Because, so that's the pipeline you see on the bottom. You cancel a transmission, so you're not sending the SSPs or whatever. If you do that once, it's okay, but after a certain time, we will lose sync. So usually you recover okay? But sometimes, so you have different timers until you get to a radio link failure. At any of the stages, you can actually resync your UE with the G node B, but if it actually, the channel is occupied for too long, you will eventually lose sync. You need to establish a new radio link, and then there's another bandwidth part you can fall back to. That's configured in the RRC layer, or this configuration file. So this is what's in the standard. Now, we were then looking at a comparison between this and Wi-Fi, just because what I will show you afterwards is a comparison with Wi-Fi, or as a coexistence with Wi-Fi. Okay? Again, what we expect from the 5G NRU is that we can use, okay, we know we have to acquire the channel, but after we have the channel, we expect to have the capabilities of 5G, okay, on top of the unlicensed spectrum. There are several challenges to this because you have to do the clear channel assessment, but you will be competing with Wi-Fi, which will also be doing its own clear channel assessment if you are coexisting. And while 5G is slotted, so if you want to sense, you have specific timings for sensing, you have specific slot timings for sensing. Wi-Fi doesn't have any frame structure. So it's sensing all the time. If it is free for, I think, 16 microseconds, will transmit. So if you have a free slot that is longer than the 16 milliseconds, it is going to go over you again. So, and this is why we had this comparison. So Wi-Fi doesn't have a frame structure, which gives it an advantage against the 5G. It also has kind of a low reaction latency, which we don't have in 5G, again, due to the frame structure and to the interaction in the software stack. It's it's not synchronized. The UE, in case of 5G will regularly send these SSPs, at least, to keep sync. And then the channel deferral for Wi-Fi is also easier in the sense that they usually look at the preamble of what they observe, and they know the duration that they have to stay silent for, and then they will start sensing right at the end when the channel becomes free. So Wi-Fi is sensing all the time. Whenever it gets free, it will sense and transmit if it can. 5G will not do that. We have, again, this slotted, this TDMA, which will actually give new radio the capability to, after it acquires the channel, to not have competition and contention among the 5G stations, is again a downturn against Wi-Fi, because Wi-Fi doesn't care and will just, if it finds a free spot, will transmit. So even if you are using a slot, only part of the slot, and the end of the slot is free, Wi-Fi will get in there. Okay. So after looking at this and analyzing this, we started doing designing and implementing 5G NRU for OAI. This is a listen before talk pipeline. So if we are operating in the licensed spectrum, we don't. Well, we do. It's OAI. If we're operating in the unlicensed, we do listen before talk, starting with a clear channel assessment. It's an energy detector. And if it's free, regular transmission. If it's not free, we adapt the transmission. Either we cancel it, or we adapt the number of resource blocks we are using to the occupied the channel occupied as, or source sensitive as occupied, sorry. So a couple of things are not in the standard about the clear channel assessment. It's an algorithm, it's not standardized. Okay, you need to set when to do it. So you have your frame, it's your TDD frames. You need to decide when to sense the channel. We are doing it in the first slot of the uplink. We are doing the sensing only on the G node B side. So everybody's quiet at that time. So this channel is empty. Well, should be empty from the G node B perspective. And if it's so, it's an easier situation for the energy detector. So you have a threshold-based energy detection in that slot. This is configured using this sleeve this is also part of the standard. And this is used because this avoids changing. So we try to minimize anything we had to do that would not be standard compliant or that would need to change the already implemented OAI functionality, because this makes our life easier. It also makes it more usable and easier for people to adopt it downstream. So we ask it for sensing. And the second thing is how, as I said, we do an energy detector. So we ask for which specific blocks should be sensed. These are the blocks that are going to be scheduled. And then we sense the channel. And this is also, we get an information about which resource blocks to sense based on the Wi-Fi channel. So this is designed for coexistence with Wi-Fi. Okay? So you can then channel, in that case over there, we'll get that channel 40 is occupied and channel 44 is empty. That would be the feedback. This, by the way, we are trying to characterize that at this moment. There is a trade-off in this energy detection, which is between the footprint, the implementation footprint, the speed of the detection, and then the accuracy of detecting. Because you can downsample, but then you lose accuracy. You need to adapt the threshold to your sampling or to your undersampling, or whatever. Now, after you sense it, you need to adapt your transmission in case you sense something. That's the upper branch. And you have two options. If you are coexisting with Wi-Fi on channel 40, you just reduce the bandwidth of Wi-Fi. That's what you see on the right. You see it on the left-hand side. We did this in cooperation with Always Smart. This is the new implementation, actually, that we were showing yesterday in the demonstration. This is what we could see. So we reduced the Wi-Fi bandwidth. If your Wi-Fi has, so if you have a Wi-Fi with more than 20 megahertz, it's going to collide with all your bandwidth, and it just cancel the transmission in that case. There was something, well, never mind. And then something else that was done is just to keep the UE in sync. We always keep, even if you adapt the physical resource blocks, you always keep 24 for the synchronization to avoid the, well, this reduces the probability that you lose sync with the GNOD. Finally, there's on the Mac layer, we also are adapting the hybrid ARQ and integrating this in the OAI box. Again, this was at the demo yesterday. And now, one limitation of this, we are doing all of this in the DU. This adds latency to the sensing, so the clear channel assessment. So we need the samples, they are sensed on your SRP, this is our setup, and they need to be transmitted to the PC, and then the DU decides something, and then it sends or not. So this adds quite a large latency, the largest part of which coming from that, the connection between the USRP and the OAI box. So this is not standard compliant, just to let you know. You need to have a much tighter sensing. Okay, we are already trying to implement this in the FPGA and try to see what is the impact actually of this latency, but well, that's what we have right now. It's not easy to go beyond this. Now, some results only. Last year, we had presented at VNC some coexistence with 822 ITS G5. Let me show you this. So this is traffic. So this is throughput on the 5G network coexisting with two onboard units. So two, well, yeah, onboard, everybody's familiar with onboard units, maybe, I guess. I hope, and what you can see is that you have the increase in traffic on the x-axis, and you see the channel busy ratio on the top, so it's increasing as you have more traffic. You have an increase in latency and the packet delivery. So the packet delivery is not really impacted, but you see the latency distribution on the ITS-5 on the left and on the latency on the NRU on the right. Okay, so just to let you, what we show with this is that you see as the traffic increases, you see an increase in latency, but it's not a very large increase, and it can still meet the requirements. So it's not dramatic, so you can actually do this, although you are not fully complying. So this is, we were sending, the traffic that was being sent were, I think, 500 byte packets every couple of milliseconds, 100 milliseconds, and then moving from 1 second going up to, so from 1 hertz to 10 hertz. So that's the frequency of the packets that were being transmitted on the ITS-G5. And so you see the latency increasing, but it's not dramatic, and so they can coexist. Now, more recent experiments is coexistence with Wi-Fi, what we were showing yesterday, and these are also the preliminary results. So if you are using only 5G, you have this full. When you turn on Wi-Fi overlapping with half of the 5G bandwidth, well, you get half of the throughput. That's not a surprise, but it just means it's working as expected. Actually, the increase in latency is not that big. And of course, if you are not doing any channel sensing, you get almost no throughput and a very, very high latency because you have lots of collisions. That is also expected. Basically, this is more a validation that it is working as we expect it to work, despite this RUDU latency. So that's hit. We have developed, validated components for 5G new radio unlicensed. These components, they can also be used for any kind of spectrum sharing. They must not be on the unlicensed band. The Digital Networks Act actually demands that the operators with holding spectrum, that they share the spectrum they are not using. And so in this case, I think we will, all the components we developed here are useful also for those use cases. We have published the code in GitHub. Next steps would like to add this to the OAI code base. I talked to Robert yesterday about this, and we will start moving in that direction, making this, integrating this. Next thing also is Philippe has been developing a skill for developing the code, so we probably will publish that until the end of the year also. As I said, we have an implementation on the FPGA, which we are validating right now, just to see how much we lose through this latency between the DU, the sensing latency. And the next step is building on top of this deterministic communication. So being able to preempt the channel and guarantee a certain maximum delivery deadline for industrial IoT applications. So, thank you.
Because coffee break is waiting. Maybe time for a question? Ready? 2 questions. Okay.
Hi, thank you for the presentation. I have a question about this system model, the USRP, the picture. So, and when you say you want to do the sensing with, I meant the other slide, but okay, this is also fine. Yeah, exactly, because I think this USRP and the other one is different. So, but you are using a B1, B200, like USB-based one, I guess?
We were using B210, but now we are using the... No, but this is a B210. No, this is not a B210. Is it? It's just spread, I think.
Okay, so my question is that...
Our UE is a B210. No, the G-Node B now is a 310. So it's Ethernet. It's a lower latency, but it's still too large.
So when you say you want to implement it in FPGA, would you do this on the FPGA on the USRP or an external?
Yes.
Yeah.
Yes. Okay. So we will get rid of those 80 microseconds over there.
Okay, so like flashing a new...
Yes, and we also get rid of the variability that we get inside the DU, because that's kind of, we don't control it.
Okay, thank you.
Yeah. that's what we are.
Other questions we may discuss this during the coffee break.
Yes, somebody else, yeah, but we can.
Discuss on the coffee break. Okay, so just stop here and looking for the discussions on the coffee break.
Thank you.